the start of group theory, symmetries. Bit of visuals always helps. We start with two-line notation. Symmetries are made up of rotations and reflections. We'll take the triangle here, where our reflections are R, S and T, and our rotations are here A and B. Right, now the symmetries of the triangle, we denote it as here S triangle. So we always have an identity, which is basically the do nothing transformation. So it's just mapping it onto itself. And we have A here, which is a rotation. So we're going from 1 to 2, 1 to 2, and then 2 to 3, and then 3 to 1, and so on. And B is the rotation here, and so on. And the reflections are, we're reflecting it in R here, so the R point, we go from 1 to 1, which is just fixed at R, and we're reflecting 2 and 3. So we're reflecting these two here for R, because R, when we're reflecting it in R, R is always fixed, and this is the point R, so it's just these two here. There's swapping places, and likewise for S and T. The columns with equal components are points, and that's an example for a triangle. Here's one for a square. It's drawn a little bit better, this. R, S, T and U, and our rotations are A, B and C, and this contains our set S squared, S square. Now we're finding composite functions, R composite A, so we go ahead for the reflection and our rotation A. So we're plugging in these values. This is R and this is A. This is our reflection. Which one's our reflection? We should have one fixed here somewhere. Oh, I've not labelled the points, have I? Anyway, we're composing these and we get our U here. So R compose A equals U, where R and A means A first, then R. So finding entries, R and A. So we go through the process here, 2, 3, no, 1 and 2, R and A. So A first, this is A, and this is R. So A first, we're going starting from 1 to 2, and then on the next one it's 2 to 3, and then from that we have to go for 3 to 4 and so on. So going through this process, and we're filling in this one, we first send 1 to 2 and R sends 2 to 3, so R composite A sends 1 to 3 and so on. So the now an inverse of A is S squared. A is this. Now A, we're mapping 1 to 2, so its inverse is 2 to 1. So the order is reversed, so it's just simply reversing the order, which rearranging equals C. So by definition we let G be a set, and O be a binary operation defined on G. Then G composite, that's our O composite, is a group if these 4 axioms hold: closure, associativity, identity and inverses. So if we look at these axioms, we can see that H is indeed an inverse element of G. Now abelian group, this is a definition of abelian. A group G composite, I want to say, the little note, the group G under composition, I think I should probably say that, that has the additional property G composite H equals H composite G for all GH contained in G is an abelian or commutative group. So this is the definition of an abelian group. Now below this, if the set G of a group G under composition is a finite set, then G under composition is a finite group. If G has exactly n elements, then we say that G composite is a group of order n. So our magnitude of G equals n. Now if the set G of a group G under composition is an infinite set, then G under composition is an infinite group and has infinite order. Now here's an example of S squared of symmetries with a function composition. Is a finite group that has order 8. So we write S squared, our magnitude is 8. So the real set of numbers with addition is an infinite group. That's just as an example. Now here's an example to show that R, our integers under addition, is a group. So we put it through the axioms. Closure for all x and y contained in our integers. X plus y is contained in R. And associativity, identity and inverses. And once we've checked all that, we will see that this is indeed satisfies the axioms and so is a group. Now example here, R star under multiplication of the reals. So closure will test if this is a group by going through the axioms. Closure here, associativity, identity, inverses. So once we've checked all of these, we've determined that this is indeed a group through our axioms. But R, our reals under multiplication, is not a group, because as we'll go through these axioms again, for all xy contained in R, x multiplied by y contained in R, associativity, multiplication of real numbers is associative, and our identity, we have 1 contained in the reals, and for all x contained in the reals, x multiplied by 1 equals x equals 1 multiplied by x, so 1 is an identity. Now inverses, now 0 is contained in the reals but has no inverse under multiplication. This is because there is no element y contained in R such that 0 multiplied by y equals 1. So the axiom fails, hence R under multiplication is not a group. Please like and subscribe, and sorry for that interruption.